Today I want to talk about estimates near the exceptional curve. So let me just give a brief recap. So the situation I want to consider is we have M omega naught is a Kähler surface. And let's assume, we assume that the Kodaira dimension is not equal to minus infinity. So this sort of rules out some behavior we don't want to consider. And let's, for simplicity, I want to assume that M is non-minimal, but for simplicity I'm just going to assume we have one exceptional curve. Let's assume M has just a single minus one curve. Which I call E. So this is a smooth rational curve. It's biholomorphic to P1, and it has self-intersection minus 1. So we consider the Kähler-Ricci flow. ddt of omega is minus Ricci of omega, where the initial metric is omega naught. And then last time we showed, so last time we showed that this the flow exists on a finite time interval, and we have a singularity at time capital T. And moreover, we know that omega t. Let me see. So what I called alpha, which is omega naught minus capital T times the first Chern class. So this is the limiting class. So this is alpha. That this is the pullback of a Kähler metric. It's the cohomology class of the pullback of a Kähler metric on N. It's omega N is Kähler. On N. So this is the limiting class. So omega T, the cohomology classes of the metrics omega T, converge to this class alpha. And so where pi is going to be, in this case, just the blowdown map. So pi of E is say y naught, so it blows down E. So the picture we have is we have a manifold M, and we have a map pi, and here's my exceptional curve, which is a P1, and pi sends E to Y, and pi is a biholomorphism. So pi from M minus E to N minus the point Y, this is a biholomorphism. Okay. So last time on Tuesday I showed that, so last time I also showed that omega T converges to a metric omega T smoothly on compact subsets of M minus E. Okay. So omega T is a smooth Kähler metric on M minus E. But it's going to have singularities on E of some kind. Okay, so what I want to do today is, so that's the setup. Okay, so what I want to do today is I want to look at estimates near E. So it's convenient to so since we have estimates on compact subsets away from E, I can actually just sort of focus on just a neighborhood of E. And work. I can just work locally. So I can actually work locally. I'll explain that in a second. So we'll work locally near E. So let's define, I'm going to write D for this ball, which is, I just look at Z1, Z2 in C2, such that Z1 squared plus Z2 squared is less than 1. So this is just an open unit ball in C2. And this I identify with the neighborhood of Y. Okay, so this is my D. Okay, so I identify with the neighborhood of Y, and I take Z is 0 corresponds to Y. Okay, and then I want to look at the blow up at the origin of D. So this, by definition, is those points Z1. Well, let me just write ZL. It's these points in C2 cross P1, such that Z lies in L. Okay, so remember that P1, CP1 are the lines in C2, and so it makes sense to say that a point in C2 lies in a line in C2. Okay, so this is by definition, the blow-up, and the map pi. So let me call this. I'm going to call this D tilde. And the map pi is simply the map to C2 to D, given by pi of ZL is Z. Okay. So we have this. Let me draw D tilde like this. So I have this exceptional curve here, and then here's D with the origin here. Okay, so pi of E is 0, where E is just, by definition, just pi inverse of 0. And this is a copy of P1 because these are all of the points. Right, these are all of the lines which contain 0. So they're just all the lines in P1. And it corresponds to 0. Okay. So now I want to. So on D we can just write down the Euclidean metric, which I write as omega Euclidean, which is just the sum I goes from 1 to 2 of dzi wedge dzi bar. Just the Euclidean metric. Okay, maybe I generally divide by 2 pi, so I can do that. It's the Euclidean metric. It's important that I need reference metrics. So I have this metric on D, and so on D tilde we have the pullback of the Euclidean metric. But there's another metric on D tilde. Maybe I didn't really want to write that here. Okay. And that is, you can map this to P1. Let's call this map P. And the map is simply given by the projection onto P1. So P of ZL is equal to L. So I have a projection onto P1. And then, of course, I have a metric on P1, which is the Fubini study metric. So recall we have so omega P1, this is the Fubini study metric. And it's given by dd bar log of well, okay, yeah, like one plus z squared, I guess, if z is a coordinate, on P1. But now what I can do is pull that back to D tilde, what I want to do is I want to define a reference metric. Define a reference metric on d tilde. I'll call it omega tilde, and it's going to be the pullback of the Euclidean metric from here, plus the pullback of this Fubini study metric from P1. Right. So the point is that the Euclidean metric is degenerate along E. And I want to get some reference Kähler metric on d tilde. So if I just pull back the Euclidean metric, it's not going to be a Kähler metric. It's going to be degenerate in these directions of E. So I want to put back some positivity in the directions of E. So to do that, I'm just going to pull back the Fubini study metric from P1. And now this is a reference. This is a Kähler metric. Okay, this is Kähler on d tilde. And in the coordinates, so in the z1, z2 coordinates, so if we work away from E, this one will simply look like dd bar log of z1 squared plus z2 squared. Okay. And now you can write down what this is. In fact, this is again there's a factor of 2 pi. So this is a way, on z non-zero. But this you can write down as follows, and this is important. Let me write it in the following way. I can write this as delta ij minus zi bar zj over r. I'll tell you what r is in a second. dzi wedge dzj bar. Where this r squared is simply z1 squared plus z2 squared. Okay, so it's just an elementary calculation. This is another formula for the Fubini study metric. Okay. So now here's the point that I want to make, is that if you write down this omega tilde, so this is a crucial inequality I'm going to use. This is bigger than the pullback of the Euclidean metric, obviously, because this is non-negative. It's the pullback of a metric. On the other hand, this I can bound by a constant times the pullback of the Euclidean metric divided by r squared. Because what you see is that this, this is certainly less than just the Euclidean metric divided by r squared. And now so this means that if I go back to M, what this is telling me is that omega naught, which is like my reference metric on M, I can bound by a constant times the pullback of omega n over r squared and the pullback of omega n, where this is defined just locally. Right, so this is near E. Okay. So the point is that that omega tilde is equivalent metric, because I'm just fixing coordinate patches. Once I fix the coordinate patches, omega tilde is equivalent to omega naught, and the pullback of the pullback of the Euclidean metric is equivalent to the pullback of any metric. I just take any metric omega n is equivalent to this. Okay, this is on d tilde. Okay. So now I can prove my first estimate. So here's the lemma. So I claim that there exist constants c and delta which are positive, such that on m minus say, let's just work on d tilde minus e. I have that omega of t, the solution of the Ricci flow, is bounded by a constant over r squared, and then the pullback of omega n, which I could also write as the pullback of the Euclidean metric. It would be equivalent. And number 2 is that omega t is bounded by a constant over r to the 2, 1 minus delta. So I get a little bit of a gain, but then I replace the right-hand side by omega naught. So I have these two estimates, and these are very important estimates. Okay. Maybe I need to, before I give the proof, let me just do some recap. Okay, maybe I need to keep that. Okay. Okay, let me go here. So let me just recap a little bit some of the estimates that we have so far, because I'm going to use them. Okay, so recall that the Ricci flow is equivalent to the following parabolic complex modular pair equation. Dphi dt is log of omega hat t plus dd bar phi to the n over capital omega, where phi at t is 0 is 0, where capital omega is a fixed volume form, and omega hat t by definition is 1 over t minus t omega naught plus t the pullback of omega n. That's a reference metric. And omega is a fixed volume form. It's not really important exactly what it is. And then last time, and so the point is that omega t is the solution of the Ricci flow is just this reference form plus dd bar phi, where phi is a smooth function. So last time, so we showed several things. So we showed that phi is bounded. We showed that phi dot is bounded above. And this implies in particular that the metric, the Kähler metric omega, I'm writing omega for omega t, this is bounded by a constant times fixed volume form. And we showed that that omega is bounded below by a constant times the pullback of omega n, for some c positive. And is that about it? Yes. Well, we also had this kind of what I call the classical estimate. Which is that if you look at ddt minus Laplacian, and when I write Laplacian, I always mean with respect to the evolving metric of log of the trace of omega. Well, omega, I could take this to be any fixed metric. Let me call it, say, omega hat, say, omega. This is bounded by a constant times trace of omega hat for any fixed Kähler omega hat. Okay. So this estimate goes back to Yao in the parabolic cases due to White and Tsao. Okay. So let me recall those estimates. Now let's go back here. So what we're going to do is we're going to use the maximum principle, and we're going to consider the following quantity. So I want to consider the quantity. I'm going to take an epsilon positive. In the end, I'll let epsilon go to 0. I want to write q epsilon is the log. So it's a little bit complicated, this quantity, but not too bad. I take the log of the trace of omega with respect to omega naught, but then I add a term, let's put a large constant a, times the log of r to the 2, 1 plus epsilon, times the trace of the pullback of omega n of omega, take that log, and then minus a squared times phi, where a is to be determined. So a is going to be uniform, independent of epsilon. A is uniform to be determined. Now, you might worry about this definition because this guy is not a metric. So the pullback of omega n is not a metric on M. It's degenerate along E. So this only makes sense on it away from E. It only makes sense away from E. So you might worry, well, what's going to happen to this quantity on E? But then the point is that the Q epsilon goes to minus infinity along E. And so what we're going to do is we're going to bound this quantity from above. Now, it's not completely obvious why bounding this from above gives these, but I claim it does. So I claim once you bound this from above, it'll give both of these. So I want to apply the maximum principle, and I claim that it goes to minus infinity along E, which means that the maximum cannot occur along E. So why is that? This is because if you look at this trace, you're taking the trace of omega with respect to omega to the n. So really I'm doing 1 over this metric. I'm taking the inverse of this metric. But now the pullback of omega to the n is bigger than r squared times omega naught. So this is, it goes the other way now. I have to put an r squared constant times r squared, the trace of omega naught omega. Over r squared, sorry. Okay, because the inverse, take the inverse of this. The inverse of this is bounded above by the inverse of this, but then you have an r squared, and the r squared goes in this direction. But on the other, so then if you put an r squared here, r to the 2, 1 plus epsilon, you get an r squared 1 plus epsilon. You get a constant times r to the epsilon, trace omega naught omega, and this goes to 0 as x tends towards E. Because remember that R, what is R? R is just the distance from the origin. So I can sort of think about D. I'm working on D. Away from 0, this is biholomorphic to D tilde. And as you tend towards 0 at 0, you're tending towards the exceptional curve. And so what you see is that as you go towards the exceptional curve, the R goes to 0. So this goes to 0. So when you take log of it, this goes to minus infinity. Okay, so the whole thing goes to minus. And phi, of course, is bounded. And this is not degenerating for any fixed t. So for any fixed t, this goes to minus infinity. Okay. So now we're going to apply the maximum principle, as I said. So let me go here. Let me erase this now. Okay, now you've seen the argument. So let's compute d dt minus Laplacian of q epsilon. So from the first one, we're going to use the classical estimate, and that says that this is bounded by a constant times the trace with respect to omega of omega naught. Okay, so from this one, just apply the classical estimate, I get this. Next, I get the estimate where I get a log of R2 1 plus epsilon, and this doesn't depend on t, of course, so I only get the Laplacian. So when I get minus the Laplacian, I'm going to get minus, that's the same as minus the trace of dd bar of this. So what I'm going to get is, let me pull down the 1 plus epsilon. I get minus a 1 plus epsilon, and then the trace with respect to omega of dd bar log of r squared. Notice what this is. This is just root minus 1 over 2 pi dd bar log of r squared. So this is exactly just the pullback of the Fubini Studi metric on P1. Okay, so that's what happens when the Laplacian lands on this term. Next, the Laplacian can land on this, and I get an a log, and then I apply the classical estimate again, and I just get a constant times a. I could take them to be the same constant. Trace, and then omega, and then the pullback of omega n. Right. And then I get the ddt minus Laplacian landing on here, so I get minus a squared phi dot, and then I get plus a squared times the Laplacian of phi. Okay. So now I want to right. So now what I want to do is okay. So I use the fact that this Laplacian phi, remember, this is the trace with respect to omega of omega minus omega hat t. And now this you can write as, this is just the complex dimension, which is actually just 2, but I write n for the complex dimension, minus the trace omega of omega hat t. Okay, so I have this. Okay, let me go over here. I want to kind of leave that up there for the moment. Okay, so now, but now what I want to do is choose my A. So I want to choose the A so that that if you look at if you look at A squared times omega hat t, so I get a good term like this, minus. Plus a times 1 plus epsilon times the pullback of this Fubini Studi metric from P1 minus a times c times the pullback of omega n. I want to choose this. So this is as bigger than. I want to kill this term. So let's say that this is bigger than constant. Let's even add a 2. Times the trace of omega naught with respect to omega. Okay. I want to choose a sufficiently large so that this is true. And why can I do that? Well, I can do that because so recall that omega hat t is bigger than some small constant times the pullback of omega n, some c positive, by definition. Now, omega hat t, it is degenerating, because this is degenerating, but you can always get this bound. So this can certainly kill all of this easily by choosing the A large. But then when you combine this with this, you get an omega tilde, which is equivalent to omega naught. So you get a little bit of this plus this. Any sort of combination of those, you're going to get a times this plus an a times this is going to be enough to give you an omega naught, which kills this term. If you choose the a large compared with c. So I'm going to do that. Okay. So go back to this, and then what we see is. So we get And then what we get is that dt minus Laplacian of this q epsilon is bounded above by, so I get minus twice trace omega naught, and then minus a squared phi dot, which is just log of omega to the n over capital omega, and then plus a squared n. Okay, so what we're doing is we're using this term, which has an a squared in front, plus this term to kill this term and give us 2 left over. Okay, so let's write this as minus trace omega naught minus trace omega naught minus a squared. Let me just rewrite this as log of omega to the n over omega naught to the n plus a constant. So I can just always, this is just some fixed volume form, I can just replace it with this fixed volume form, and it would differ by some constant which depends on a, but a is fixed now, so it's uniform. And now I claim that this guy is actually bounded because if you were to write omega naught, or say g naught is just the identity, and g is diagonal with entries lambda 1, lambda 2, then you can see that this trace of omega naught plus a squared log of omega n, again n is 2 here, this is nothing other than simply 1 over lambda 1 plus 1 over lambda 2 plus a squared times the log of lambda 1, lambda 2, which I can write as 1 over lambda 1 plus a squared log of lambda 1. Well, let's say this is just the sum. I goes from 1 to 2 of this. And now I claim that this is bounded below because lambda i's, you don't control the lambda i's, but if the lambda I was going to 0, this is going to infinity much faster than this is going to minus infinity. And if lambda I is going to infinity, this goes to 0, this goes to infinity. So this is bounded below. So minus it is bounded above. So this is bounded by minus trace omega naught plus some constant. Okay. So then that implies that the trace of omega naught with respect to omega is bounded above at the maximum. So of course I'm computing everything at the maximum of, so at the max of q epsilon. This is bounded above at the max of q epsilon. Of course, I should be a little bit more careful because this quantity q epsilon is only defined locally because the r is just a local quantity. But so you might worry, okay, what happens if it's achieved at the boundary of that neighborhood? But it's fine because we know that everything is bounded on the boundary of the neighborhood because we have C infinity estimates on compact subsets away from the exceptional curve. Okay. So now that I claim that should imply that well, let me leave that. So that should imply that that Q is bounded. Right, so this implies that Q epsilon is bounded above at the maximum. And why is that? Well, that's because this quantity, I guess from what I erased, because remember that r squared times the trace of the pullback omega n omega, this is bounded by a constant times the trace of omega naught omega. And so if I know that this is what bounded, then this is also bounded. And phi, of course, is bounded. Okay. So now, so Q is bounded at the max, and then hence everywhere. And now we let epsilon go to 0. And we get that, that this quantity Q, okay, so maybe I'll erase this. So now let epsilon go to 0, and what we get is that the log of the trace omega naught omega plus a, and then log of r squared. Of course, none of our estimates depended on epsilon. This quantity here is bounded above. None of our estimates depended on epsilon. The only reason I needed the epsilon is to ensure that I didn't get a maximum at the point on E. Okay, so now I claim that I have these two estimates now. Okay, so why is that? Well, for one, to prove one, what I notice is that if I look at that r squared times the trace of the pullback of omega n with respect to omega, again, using this several times, using this inequality here, this is bounded by the trace of omega naught omega. And so what we see is that this guy then therefore must be bounded, because then the log I could just replace this by the log of this, and so what I get is that r squared from this inequality, I get that r squared of the trace is bounded, and that tells me that that if you rewrite this, that omega is bounded above by a constant over r squared times the pullback of omega n. Okay, so that implies 1. So we've proved number 1. And then for number 2, number 2 is perhaps not quite so obvious. For number 2, what I can do is the following. So I use the fact that the trace with respect to omega naught of omega is bounded by a constant times the trace of the pullback of omega. Now remember that the pullback of omega n is going to 0 along E. And so this is a bigger thing because you're taking the trace of a metric which is degenerating along E. So I claim that that's true, and in fact that it follows exactly from this. Oh, maybe I needed a constant here, right? Maybe I need to divide by a constant. So it follows from this inequality. Okay, so how do we use that? Well, now what we see is that if you look at the trace of omega naught omega to the power a plus 1 times r to the 2a. Let me go back here. Maybe it's easier just to exponentiate this. So guys, go back here. So this is what we have. This is the inequality which holds everywhere. If you exponentiate, you notice you get trace omega naught omega times r to the 2a times trace the pullback of omega n omega to the a. This is bounded by a constant. The a squared phi is just bounded. So I have this inequality after exponentiating. But then this is just bounded by, certainly bounded by trace omega naught omega times the trace times r to the t times r to the 2a times this trace of the pullback omega n omega to the a. If I put a constant there, and then we said that this is just bounded. Okay, so I'm using this. But then you see that if you just now rearrange this a little bit, I get that the trace of omega with respect to omega naught is bounded by a constant over r to the 2a, and then you just raise this to the power 1 over a plus 1 over a plus 1, and this is some constant over r to the 2, 1 minus delta, where the delta is 1 over a plus 1. And that exactly tells you this, that omega t is bounded by constant omega naught over r to the 2, 1 minus delta. Okay, and this little bit of delta is crucial for our estimates, shortly. Okay, so now we have so we've proved these two estimates. So now I want to prove some more geometric estimates. So we have the following, let's say, theorem. So along the Ricci flow, we get, number one, we get the diameter of the whole manifold with respect to the evolving metrics along the Ricci flow is uniformly bounded. So when we have this singularity, it's not so bad. We know at least that the diameter is bounded. And moreover, if you take the diameter of the exceptional curve with respect to omega t, so of course I'm restricting omega t to the exceptional curve, this goes to 0 as t goes to capital T, and it goes to 0 at least at this rate. This is not optimal. But that's what we can do. It should probably be to the power 1/2. Okay, so what's the proof? Well, at least I'll start the proof, and then maybe the next lecture I'll finish. Okay, so first of all, I'm going to use these estimates. So we only need to work on D. So we just work on D tilde, which is isomorphic to D, the unit. It's just the unit ball. I think I tend to think of just working on the unit ball, where the origin gets replaced by the exceptional curve. So D tilde is where you replace the origin by the exceptional curve, but away from the origin they're isomorphic. So I work on D tilde. We identify with D outside E. So I want to say that so it's sufficient to bound distances in D, because I know outside of D we're working away from E, and therefore we have all the estimates we want. So everything is bounded there. So the first thing to do is let's take P and Q. First, suppose that P and Q are distance r from the origin, or from the exceptional curve, if you like. So suppose I take 2 points P and Q, which are here's the origin. Take 2 points P and Q, which are the same distance from the origin. So in other words, work on D. So in other words, P and Q lie in the 3 sphere of radius r. Right? So this is the 3 sphere in C2 of radius r. So first take those 2 points, and I want to show that they're always a bounded distance away from each other. But this is easy, because if you take the distance just with just with the Euclidean metric between P and Q, then we know that they must be bounded by the diameter pi times r. Okay, just in the Euclidean metric. But then if you take the distance on SR and you take instead the metric G of t, well, we know from our estimate number 1 that G of t is bounded by the Euclidean metric over r squared. And so this is just bounded by constant over r times pi times r, because from 1. Remember that distance goes like square root of metric. And so you have to take the square root of the r squared. I get 1 over r. Okay, so this is just bounded. So what it's saying is that the distance between P and Q, the distance then between P and Q has to be less than a constant. Okay, this is just a very crude bound. It's not a very good bound, you see, because you can see that if P and Q were very, very close to the origin, they ought to be very close to each other, but this bound is just saying they're bounded. It's not a very good bound, but it's good enough for the moment. Okay. On the other hand, if we let me leave that lemma. Okay, so I'm trying to prove damages. Right. On the other hand, let's look at a radial path. A radial path, say gamma of lambda is, say, lambda x. So what I want to do is now, again, work on D, just the unit ball, and take a path, take any point x in D, so x is some point in D, and I just look at this radial path, gamma of lambda. So lambda is a parameter going from, say, 0 to 1. Let's sort of imagine we're not actually hitting the origin. If you look at that path, then you can see that the length of gamma, which I write as L of gamma, is just the integral from 0 to 1, and then you take the square root of the metric G, take the length of gamma with respect to G of t. I take G of t at the point gamma of lambda, and then I get gamma prime d lambda. Okay, now I'm going to use estimate number 2. Now estimate number 2 tells me that omega t is bounded by this constant over r to 1 minus delta. But I'm going to replace this omega naught by the pullback of the Euclidean metric plus the pullback of this Fubini-Studi metric. And now I'm going to use a crucial fact, which is that the pullback of one can easily check that the pullback of the Fubini-Studi metric is 0 in the radial directions. So this is 0 in the radial directions. So you take a radial path, the tangent vector in that radial direction is just going to vanish when you restrict to this pullback of P1. So that means that actually when I restrict to these radial vectors, I can just ignore this one. And then from this, I'm just going to get a constant times I'm just going to get the integral from 0 to 1, and I'm going to get 1 over so I'm going to get 1 over this guy, but r is the distance, which is just lambda times x. So I'm going to get 1 over lambda times x to the 1 minus delta, because I'm taking the square root, so there's 2 1 minus delta becomes 1 minus delta. And then I just get the Euclidean metric applied to gamma prime, but gamma prime is just x. So I just get x squared, if I take the square root, so I just get x. Okay. So let me say it again. Using this inequality, I can ignore this bit. I just get the pullback of the Euclidean metric over r to the 2 1 minus delta, because I'm looking at the radial path. And now g of t is bounded by, so I get 1 over r to the 2 1 minus delta. I'm evaluating at a point gamma lambda, which is just lambda x. So I get, the r becomes just the norm of this, which is lambda's positive, times norm of x to the 1 minus delta, because I'm taking the square root. And then this now just becomes the Euclidean metric evaluated at gamma prime, which is just x, x. So this is just the length of x. And then you see that this is, there's a parenthesis. I'm missing the parentheses there. That's my r. And now the point is that I'm integrating in lambda 1 over lambda to the 1 minus delta. Well, that's an integrable function in lambda. So this is bounded by a constant, and then what you're left with is simply x to the delta. And that's bounded, but not only bounded, it actually goes to 0 as s goes to 0. Okay. So maybe that's a good place to stop, and then in 20 minutes I'll continue. I'll finish the proof of the theorem. Thanks.
Is that where you use the Taylor circle to any dimension of the
This works you can do this in any dimension where you replace the curve E with an exceptional divisor. So you can.
So why you don't need the last part, you don't need the dimension. You don't need a 2 dimension.
You don't, for these estimates, no, I didn't really use 2 dimensions, I don't think. I didn't really use 2 dimensions. I would replace P1 with a Pn minus 1. Yeah.
So where do you use 2 dimensions?
Well, I use 2 dimensions just for the setup, actually. Just to say that when you start with a Kähler surface, if you have a finite time singularity, then it is going to be low down an exceptional curve. In high dimensions, there are other possibilities which are much more complicated, and we don't know how to deal with those.
Okay. So the first part you need a...
Just to say that there exist these exceptional curves, and those are the ones you blow down, you're using dimension 2. Yeah.